Hello, it's me again. I'm Nafid. Today, in this video, we will talk about the configuration or the third part of the configuration of FlexFabric. In this part, we'll talk about access control lists, we'll talk about the quality of service, and we'll talk about the stacking single control plane we call IRF or Intelligent Resilient Framework. Let's have a look. Access control list. Objectives of this module to understand what is access control list, the types of access control list, and what do these access control lists consist of, how HPE Comware applies the access control list, and what is the typical behavior. And we'll look at some implementation scenario based on the type of the access control list. So access control list, as the name indicates, is to be able to control the traffic, either permit or deny based on certain criteria, and we would like to have a more control of our traffic when it ingress or egress our network, whether that traffic is switched traffic or routed traffic. Now typically we have three different types of access control lists when it comes to Comware. There's a basic ones, there's an advanced ones. Obviously basic applies only to the source of the IP traffic. Advanced can be applicable to so many criteria, including IP, TCP port, UDP port, VPN, quality of service, multiple different things. And for the Ethernet or the frame or layer 2, also something similar to what we have just said. And it is applicable to the MAC header basically, and obviously there are certain criteria. Now in terms of basic access control list or standard access control list, they have number ranges from 2000 to 2999, and that's a range of numbers or IDs. You can also give a name to the access control list. Maybe it makes more sense. Sometimes you might want to match the number with a VLAN ID and maybe describe the access control list to understand what does that ACL meant to do. And in the case of access control list that is basic or standard, we need to have rules and actions, obviously. Now in the rule, you can identify the rule by any source IP or specific IP or a range of IP, but only on the source. You cannot have anything on the destination. And in the world of access control list, there's something called inverse mask or wildcard bits. Simply speaking, it's the inverse of the subnet mask. So if I would like to focus either permit or deny this range, for example, it means that I am going to say, okay, the first part of the first 3 octets must match. I will use zeros in the first 3 octets, and in the last octet it can be a range between 0 to 255. I will put 1. This is similar to the case whereby you can have subnet mask, normal subnet mask, and the host portion and the network portion, but you reverse it. The ones in the subnet mask become zeros, and the zeros in the subnet mask become 1 if you would like to. And you can have the flexibility, you can control basically the way it works. You think about it again, the reverse of the mask. So that's subnet mask and that's the wildcard. So the reverse of the mask. And the way it works, so whatever 0, it has to match. So you think about it like that the octet, the value of the decimal value is you subtract from each other will become 0. 1 minus 1 will become 0. 10 minus 10, the third octet, 0. And here 255 minus 0 will be 255. So that's how we probably understand, or different way to understand the wild mask. So now there's something different in Comware. So let's say the packet comes in and there's an ACL applied to the interface, and that's going to test. So the packet, does it match any criteria? The answer is yes. Perform the action with a permit or deny. No match the first criteria, they move on to the next. Is there any match? Says no. Then continue the next one and next one, next one. If at the end there's no match, in Comware it's completely different. Most vendors will go implicit deny. In Comware they will do implicit permit, meaning if there's no match, unless you explicitly deny the traffic that doesn't match any criteria, by default the traffic will be permitted. Any match will perform the action and no other criteria will be checked. Now in Comware also we have so we have typical behavior basics. So when you create an access control list, it will be assigned an ID. So we'll be starting from, by default, the space is 5, and they will start from 5, then 10, 15, 20. This is every time you add a statement inside the access control list, it will be implicitly assigned a number. You can change that. We could the step or the jump or the space. We can space it out like 10, for example, and you can insert, so you can reorder. You can also, if you think that there's a statement needs to be readjusted or inserted, you can also insert the statement or access control entry if you would like to edit the access control list. Now there's another way in Comware that is very specific to Comware. We call it auto mode. And the auto mode, it doesn't initially look at the rule ID or the sequence. It will initially look at the VPN instance, and if there's no VPN instance, it will look at the rule that has more zeros, i.e. more specific in the source IP, so the longest match if you like. And if once that's finished, then it will look at the smaller rule ID. So from rule say 5, 10, 15, 20, 25, and so on. So that is a possibility, and that's a unique feature inside Comware. We call it auto mode. Next one will be advanced or extended access control list. That the number ranges between 3000 to 3999. Again, you can give it also a name. In this one, as the name indicates, we can have the flexibility. So you can be based on protocol, we can be based on some sort of TCP, UDP port, source destination, and you have a huge flexibility in this case. You can create things like based on ICMP protocol, layer 4, IGMP, PIM, OSPF, and much more. And you have extreme flexibility based on the source, destination, and different actions, as well as extended action. Now also we have auto roll. Again, remember, we have implicit permit any at the end of the access control list in all Comware and all types. So they will, if you use the auto mode, if you like, they will go VPN instance first, specific protocol type rather than IP. So if you have very specific protocol, that will be tested first. Again, they move on to the more zeros in the source, more zeros in the destination, the narrower port numbers or range and TCP, UDP. You might have a range of ports, so the narrower the specific or the smaller range, then that will be applicable first. And eventually, if once they execute and look at these, they will go kind of a normal behavior, smaller rule ID. So we have that flexibility with the auto mode. The third type of access control list is also called MAC-based or Ethernet frame header, ACL. The range will be between 4000 to 4099. And again, the match criteria, this is like an advanced access control list basically, but this MAC. And that's one type. We have source, destination, protocol, and we have flexibility. Now, in the world of MAC, the match will be if hexadecimal, and do not match hexadecimal 0. So it's the other way around. It's not similar to the IP based. So it is, if you say if is similar to, it's a hexadecimal value, isn't it? And 0 means don't match, and you don't care, basically. So this is when you need to have a range. How to apply ACL? You can apply it on the routed ACL as a layer 3 VLAN input in and out, and you can apply static port ACL as well, in and out. So if you look at the routed ACL, you can apply it in or out. So that is apply the routed ACL to control traffic at the VLAN boundaries. So the routed is VLAN boundaries, and you can apply one per direction per interface. So you can have one in and a different one out. So one in, and you can't apply the same one out, so there will be a different one out. And that's a criteria which traffic that is processed and filtered with permit or deny, and which traffic is not filtered. You can also apply the ACL as a port ACL. So you control the traffic on the physical interface. Again, you have one port per direction per ACL. You can apply to link aggregation as well. So you can apply it in on a layer 2. It will filter all inbound traffic routed and switched on that physical port. You can apply out for both layer 2 and layer 3. So you can filter the switched traffic or routed at layer 2, and you can do the same for layer 3, of course, by definition is routed. You can create what's so called also an active control list. Rather than part of that one, you can apply quality of service policy. So you can filter traffic using access control list by create a quality of service policy. That policy can be applicable for globally. You can create and then apply globally, or you can apply it to the specific interface. That gives you probably different dimension or different way or different method to apply or to control, filter the traffic, and gives you a bit more flexibility in this case. Now some example to apply ACL, basic ACL. Remember, basic ACL can only filter based on the source IP. It means when I need to apply it, I need to apply it as close as to a destination. So if you have a source, as close as to a destination to filter that source IP. In the case of advanced or extended access control list, we will apply it, or we can apply it wherever, but we should be able, or logically, we can apply it as close as to the source, and that makes more sense. You can apply things like, if you'd like to control access to management, like SSH or HTTPS and so on. You can apply also access control list on the switch if need be, and that is one way to control the traffic in this case. That's end of module 10, access control lists. Quality of service, and in this module we'll discuss topics that relate to quality of service. What does it mean to us, and some parameters within that quality of service. Now just keep in mind, in any quality of service implementation, before you think of a quality of service or QoS, you need to think of a good design. So if you have not had adequate uplinks and the design doesn't accommodate for traffic that is generated, so you have not really provided the traffic correctly and you didn't understand your network, and you have inadequate uplinks, even with the best quality of service, that will not be something that you can overcome the limitation of the bad design. That's number one. Number two, you need to think also in terms of the uplink utilization should not exceed probably 65 to 70%. If you always exceed more than 75% or 70%, again, depends on the type of the network. You need to think of upgrading and looking at how to improve the uplinks and the communication between the edges and core and distribution. Anyway, quality of service is to do with the congestion. So again, the congestion should not be a permanent behavior of your network. And the quality of service is looking after the traffic also that is susceptible to delay and jitter, things like VoIP and videos, because these tend to be small packets like the VoIP, and they are susceptible to delay and jitter, probably, of course, and packet loss. We talk about two types of traffic here, TCP and UDP. TCP can back off, can reduce the rate, can retransmit TCP, so it can tolerate to a certain extent congestion, but UDP is more susceptible to that because there's a simple no retransmission, no acknowledgement, and so on. Again, a case for traffic that is what latency is the delay in transmission. Jitter is unequal spacing. You don't want to have that experience in your network. That's why you need to think of a good design, number one. Number two, you need to implement mechanisms that can reduce that effect, which is in this case quality of service. Now, when you think about how traffic is handled in any device, the traffic comes, and in these interfaces we have also called queues. And in Comware, the queues, we call them LP, local preference. So again, just remember the queue. Once the traffic is mapped to a queue based on the criteria, there will be in the queue multiple buckets. Of course, they have to be served. We call them scheduling or scheduling of the buckets in the queue. Now, which queue you map to is locally significant only. To the other device, once the traffic leaves the switch, what matters is the quality of service you map or you attach to that packet. So whether that is a layer 2.1p or the DSCP layer 3. But which queue locally, it does not really make a difference to the other switch and to other devices, because queues are only significant locally. Now, for any quality of service, we can have either on layer 2 header, that's part of .1 queue, which is .1p, and normally it has 8 values, obviously, 2 power 3 bits. Or you can have it at layer 3 header. We call this diff serve DSCP, differentiated service code point. And we have multiple values, and typically you can define your own values, but typically there are 13 in the standard. Now, when the traffic comes to you, you either honor, accept whatever comes to you, normally between switches, or classify, so you can look at that and say, okay, my endpoint that is sending me traffic may be marked with certain value. I don't want to honor, i.e. I will not accept. I would like to redefine the criteria or redefine the parameters inside that bucket. Now, if you honor in Comware, .1p, which is basically layer 2 tag, there's a default mapping between the layer 2 tag and the queue. That's a default mapping. So the mapping between .1p and the queue for the best effort traffic, background, scavenger traffic like FTP, and other types of traffic, they will be mapped to the certain queue. And of course, the mapping to the queue dictate how much attention, how much service, what is the priority for that traffic when the switch ingressing that queue. Of course, remember, one interface can be ingress and egress for other types of traffic. Now, if you think about the mapping as well, coming back to this, the values of DSCP layer 3 will be by default mapped to .1p, which by default will be mapped to certain queue. So that's for outgoing or incoming, that's fine. But remember, this mapping is default mapping. Can you change it? The answer is yes. There is no need to change it unless there's a specific reason to do that. You can indeed also reduce the queue from 8 queues to 4 queues. If you decide to do so, depends on the type of the traffic in your network. Now, I can use a classification based on certain parameters. to prioritize the traffic. I can classify. Classify means I need to look at the traffic as per certain criteria based on the port, physical port, right? I can, so I say, okay, whatever comes to that port, I will treat it this way. Or I can create a classification policy that will look at certain criteria, and I might mark or I accept the traffic as is. So I can classify or prioritize the traffic based on a port, incoming port, or a certain policy that can be based on application, VLAN, port ranges, and so on. And then I apply my quality of service based on that. Now I can classify at layer 2, or layer 3. So you can classify your traffic based on .1p or DHCP layer 3. Layer 2 is .1p, as we have seen it a few slides ago. And layer 3 is differentiated service code point that you can look at layer 3 value. So again, on the switch, you can disable the quality of service trust on an incoming port. You can globally apply it, and you can just change things on the local port. And you can say, okay, whatever comes to that interface, I will give it certain quality of service value. So I might respect the incoming traffic based on the port. So I can do based on .1p, for example, or I can do based on DHCP. So how to do, when do you use .1p? Normally, usually, if you connect to things that have tag, obviously, we would normally use .1p. If you connect to things that don't have tag, normally we will go layer 3, because layer 3 is always preserved. Nothing changes, no tag, doesn't matter. Now you can apply, so you can create a quality of service policy. And the policy consists of two things: classifier, probably access control list, and behavior. Behavior means I can remark, for example, what I'm going to do with that traffic. Shall I remark it or shall I honor it? And I can apply it globally, that policy, so it will be applicable to every interface, one policy, and you can disable it on certain ports if you would like, or you can apply it to the VLAN interface or VLAN, and you can apply it also to the physical interface. Now, you can also look at the quality of service to classify traffic in queues. You will define the classes, so what you're interested to control, define the behavior, remarking behavior, and use the policy to map the class to behavior. So what criteria and what action, and then you apply the policy. You can apply the policy based on whatever criteria and to whatever interface or VLAN that will impact how the traffic will be handled, either based on layer 2 or based on layer 3. So as we said, for the tag traffic, we will go and look at things in .1p, and for the non-tag traffic, normally we will look at layer 3 to apply the policy, either honoring it or honor the traffic, or remark it, so either classify it or honor the traffic, accept whatever values come to you. Now we know which queue to map to based on our maybe policy, and once we're happy with that, we need to see how we will serve these queues. So the queue or the traffic comes mapped to different queues, normally 8 queues by default, and we would like to see which queue to serve first and how much of that time and so on. In Comware, we have also called scheduling mechanisms. So the methods that schedule, we serve the queues. There are multiple methods: strict priority, wait round robin, or a mix, or wait for a queue, or a mix. So simply speaking, if you only base on strict priority, it means you have to serve every single packet from the high priority queue before you pay attention to the next queue. Remember, the queue is something logical, and of course there are many details which we don't cover here, but the queue is something logical on the interface, and we have normally each bunch of interfaces, they share one ASIC, and any bunch of interfaces or group of interfaces, again depends on the hardware or the model, will have shared buffer. So normally they will buffer ingress and egress, and then they will do after which they will serve the queue. So strict priority is I would serve every single packet in a high queue before I pay attention to the next one. That can lead to what's called queue starvation. So you might have a lot of drops, especially if you have a lot of high queue priority traffic, then you might lead to issues with lower priority queues. Weight round robin is I give each queue a weight, and then based on the weight I will set the number of buckets in that queue. That tend to be fairer to serving low priority queue, but I can also mix between strict priority and weight round robin. So I give certain value, the top queue 7 will be always served first, and for the rest I will use weight round robin. Remember, if Q7 starves or will have issues, then the whole network will have a huge impact. Because in Q7 we always go, for example, for things like spanning tree or SPF, anything to do with the network control, then that will be the highest priority queue. So you would rather not, would rather make sure that the top queue is always served. So I can have a mix. There's also, another mechanism called weighted fair queue. Also, that tend to be also reasonable. It depends on the types of the traffic you have. If you have large packets or smaller packets, you give each queue, and that's by default, each queue is given a weight, and then based on the weight I will fairly treat these queues, but also at the same time I will make sure that no queue is starved by implementing what's called guaranteed bandwidth. Sometimes we call it minimum guaranteed bandwidth, or MGB. I will be able to have the minimum guaranteed bandwidth also with the weighted fair queue. I have an option also to mix between strict priority and weighted fair queue. So you can have do two different groups, and the first group will be in strict priority, like group number 0, and the rest will be weighted fair queue, similar to what we have seen weighted round robin and strict priority. So you can clearly see how flexible the system is, or the devices are, and how can we mix between different types of queues. Now I have also another feature called port limiting. I might want to control how much traffic to start with comes to me, or how much I allow traffic to leave on certain interfaces. So on top of the quality of service you implement, you might want to even alleviate the pressure on your network. Maybe you're connected to your university, and to your edge of the your core come from different residency, like from students, and these students are sending so much traffic, and you'd like to control that. So this is a nice way if you like to police the traffic in a way. Now also you need to think about how much traffic I can guarantee. We call traffic policing. So in traffic policing world, we say, okay, I commit, so it's called committed information rate. I can guarantee that up to this rate, I will serve every single packet. And up to this, which is excessive, peak information rate, in between, some packets might be dropped. But above this, there's no guarantee. It might be the case there's no congestion in the network. Above PIR, maybe some traffic might pass, but there's absolutely no guarantee. And I will make sure, if I have a very busy network, anything above this one, I will drop out. So with this, it helps the rate limiting as well. So you need to think of how to handle the traffic holistically, how to reduce the incoming traffic if there's an excessive UDP, peer-to-peer applications, and so on. Once you are happy with that, of course, after you have a good design, you need to think about how much I committed information rate, and then what's the maximum possible. And in Comware, they work on also called committed bucket, or C bucket, and they kind of give a token to that. Anything that conforms to the token then will be processed. Like in this case, for example, we have 100 bytes. I will guarantee, that's just an example. Above that, I will drop, there's no guarantee. And the committed information rate bucket, if you like, I can guarantee based on the bucket size. So I will be able to say, okay, if you conform to the CIR, I will definitely guarantee that you will be served and no traffic will be dropped. Up to the PIR, in between them, some traffic can be dropped, and anything above PIR and absolutely any excessive traffic, I will drop it. And there's absolutely no agreement. So this can be used, of course, if you have within your network, of course, then you will configure these settings, or sometimes between service providers where they have certain SLAs, then they will be able to agree on certain things. There might be charges and other stuff, but also in terms of you have lease line and other types of traffic communication for the business, you will have also a guaranteed service level agreement. Then you will need to guarantee, and you have to explicitly tell what is the CIR, what's the PIR, and so on. Now, I can also look at things differently. So within the queue and between the queues, I will mark the traffic with a drop probability. The green will be guaranteed to pass. The yellow, think of this one like CIR, think of this one like the maximum PIR, and think if this one is above PIR. Discard probability, this will be discarded. Yellow, some of them might discard, others might be green. I might have different actions. I might discard. I can pass here and change the quality of service mark and so on. You have a lot of control over how traffic is handled. So generally, you will define the traffic. You will then define the behavior. So this is classification behavior. You're going to create a policy and then you apply the policy. Simply speaking, this is the way it goes. Now, if you have issues, i.e. if you have a lot of traffic, what happens normally, there will be tail drop. So traffic comes in, whatever passes, then there will be tail drop. Now, the solution to this one, random early drop. So they'll start picking traffic based on certain criteria, and they start dropping the packet randomly early. So this is, again, think of this one like CIR, PIR, and anything above that will be dropped. Now, each queue, within the queue itself, there will be drop probability. And in between the queues, so like in this case, all traffic 100% will pass. In here, 90 will be dropped randomly, will pick up random. Again, this is inside the queue. Above that will be 100% drops. So remember, in the weighted random early drop, so I will give a weight to each queue rather than all queues the same weight. And in that, I will say, okay, for the higher priority queue, only 10% of the traffic in this yellow area will be dropped, while here 25%. So the guaranteed or the amount of traffic that will be dropped in the lower priority queue will be, we call discard probability. For the DP red here, that's a queue that is lower priority than this. That's a higher priority. You will see that the green area in the higher priority queue is much higher. Obviously, for this to work, you need to configure that. So you will go through certain steps and you configure. And this is an option that you can configure in your network for scheduling and for the drop probability. Again, we go back. Quality of service will work only if you have a good design. Also, you need to think about LLDP, which we talked about, and in LLDP capable phones and non-LLDP, like things like Cisco CDP. We can handle that as well. So we can look at traffic that is generated and the communication between the switch and the devices that run LLDP. They will need to communicate what is the PVID, what's the tag, what is the default values like voice that will dictate things like what's the quality of service I will assign. The switch can communicate these parameters to the VoIP phone, and you can extend the trust here. You push settings using LLDP, and anything that doesn't run LLDP, also we can have what's called CDP. It is also supported in this case. That was the end of module 11. Intelligent Resilient Framework, IRF, or in other words, Single Control Plane Stacking, which is going to be the last module in this course. What are the objectives? To understand the technology and concept, what does it mean to us, and how to configure that, obviously. And in case of a stack split or split stack, we will use a mechanism called MAD or MAD, and then we look at a configuration example. Right. So when devices are physically connected as such, maybe two or more devices, depends on the platform, logically we will have a fabric that is logical combination, or it is a combination of multiple physical switches produce one logical device. The range between 2 to 10, it depends on the platform, and we're going to show you that soon. So benefits, there's no doubt that stacking would give you an advantage over spanning tree, VRRP, and the likes of HSRP and Cisco. Can be managed as a logical device. You don't need, to be quite honest, you don't need spanning tree if you have a well-designed network, unless there's a need for loop prevention somewhere in the network. We'll have OSPF, again, there's a single device, single global routing table, and so on and so forth. So before the RF stack, you might have needed to use MSTP, multiple spanning tree, VRRP. Once you stack, so in this case, you cannot really use any link aggregation because these switches are separate devices. But once you start stacking, once you do the stack, these four switches in this example become single logical switch. And the easy thing about the stack, IRF stack, is there's no specific interface, like there's no module. Sometimes we call front plane stacking, meaning I can have a 10 gig or 100 gig links. I can then connect the switches over even multiple buildings. They don't have to coexist in the same physical location. They can go as far as the transceiver can transmit traffic. I can then create link aggregation and make my obviously my network manageable and less susceptible to loops, and I can utilize all the links. As you know, with the link aggregation, you can have load sharing. All links are active in the same time. If you quickly compare the spanning tree with IRF, definitely IRF comes on top, and that will be the one that we would like always to push for. And if we can, as much as we can, we would rather stack than using spanning tree. Now, when it comes to platforms, probably depends on the platform. That is the largest switch in the portfolio, 12900, which is a huge switch that can be used in data centers usually, and you can go for stacking. In general, minimum requirement for the stack is 10 gig. So on these switch series, we have 10 gig interfaces required. Now for the topology, you can have daisy chain or you can have a ring topology. And the way it works, let's think of the stack or the RF port as a logical port we're going to create. So logically, we are crossing over, if you like. So what port 1 on any switch should logically connect, not physically. So it should logically connect to port number 2, stack port number 2. Again, that applies here. Think of this, port 1 connect to port 2. Port 1 connects to port 2. Port 1 connects to port 2. So the components within the RF, they are very simple to configure. It takes only a few minutes, probably depends on the switch, but probably within 10 minutes you're done because it needs reboot and other stuff. So again, you cannot connect one-to-one logical port, stack port. Yeah, you can only connect 1 to 2 as a logical crossing over. You're going to create domain, member ID, you're going to renumber some members, and then you will connect them together. We're going to show you an example. Now, the system is resilient. One of them will be a master, or the coordinator, if you like, or the conductor, and the subordinates. If the master is lost within seconds, even less than a second, subordinate, one of them becomes a master. Now, the criteria is this. Always the current master wins. So if you have a switch that's been running and you need to add a new switch, the new switch becomes a member. And the one that is running it always, which is the current master, yeah? So will always be master, will not force a reboot. And that will ensure continuous service. Member of the higher priority wins, and then a member of the longest uptime. So the precision is up to 10 minutes, so within 10 minutes. So logically, any switch you would like to become a master, you give it a high priority and then you power it first normally. And then if then the tie is the one with the lowest MAC address. So over the synchronization, they will synchronize everything. So the running config will be synchronized. All devices obtain and run the running config from the master, and that will guarantee any time a master failed, one of the devices immediately will take over. Configuration changes are propagated and pushed. The devices use their own startup config files only after they're removed. So they will always be overridden, if you like, by the master configuration. So think about it, they become logically one device. So an example, if we look at the MAC table, you're going to see a device is a member ID 3, like in this, member ID 1, member ID 1, member ID 3, member ID 2, as if they are line cards or modules in a virtual chassis switch. Now, when you have a stack, and there might be sometimes if there is bad design or something happens to the interface, the link or the physical link or links might fail, and we call this one a case of the split or stack split, IRF split. That can cause a problem because if they can't see the master, then the standby or subordinate becomes a master. Both of them advertise the same master, and that can lead to loops and loss of traffic. Now, to overcome that or to counteract that, we have also called multi-active device detection or multi-active detection, MAD or MAD, that has extreme flexibility and can be implemented in 4 different ways. The common way is very common, this one. Also, this is common. You can do ARP MAD, and you can do IPv6 network discovery MAD as well. Now for LACP MAD, remember, these 2 switches appear as if they are single switch. They will, so we assuming that we have link aggregation here. So the MAD traffic will use the LACP data units, LACP, LAC PDUs, piggyback on that. They will talk to each other. Example, what does it mean? If I am a master, I'm a subordinate, and the link is lost between the 2 devices, I don't see my master from this link, but I do see my master from this link. It means I know the master is up and the link is down. So I'm going to shut all my ports except the RF link by default and any other port that I can exclude from shutting down. So that's a default behavior. A good way to do it is PFD. So this doesn't have to be directly connected, while of course the IRF link has to be directly connected. But this can have maybe a layer 2 switch in between, simple hub, and you connect with multiple, because you might have multiple members. So you can have BFD that connects to multiple, which is a preferred method. And then you will assign IP addresses, and they kind of do a ping between them. So if they don't see each other on the link, but they do see each other on the BFD, it means I am able to guarantee that the master is physically available. I will then go ahead and shut down my ports, except the RF link and any other link that has been excluded. As best practice, we would also exclude RF link anyway, just in case. So the MAD, as we said, prevent address conflict and making sure that the link that are connected from the subordinate will be shut down, so the traffic will not be using these links, and they will always go to the correct links till the issue is being fixed. So it means that the standby or the subordinate will go into recovery mode. If RF link is fixed, then the one that, or the bunch of device, maybe one or multiple, in the recovery mode, they will reboot, will join the stack and reboot and join the stack again. Obviously the master and the active portion or active segment, it might be one or multiple, will always continue forwarding the traffic as usual. To do the configuration, so you go with the first command, RF domain, and then you will need to renumber those members. There will be 2, 3, 4. That requires a reboot, obviously. You can optionally, is recommended, have priority. So I would configure the priority on at least my master, and then I would create the interfaces. So I would shut the physical ports down, create the logical port, map it to the logical port, and map it to the physical port. So now physical ports are members. Now one logical port might contain one physical port, but also one logical port can contain multiple physical ports, 2 of them. Yeah. Then once you map it, you unshut it down, you apply the configuration. This is extremely important. Many people forget to perform that step. The next one will be saving the config for all devices, assuming that you have just maybe it might be a green field where you have new devices. You will have to reboot the devices and then connect physically. If you have physical access to the switches, physically connect them, and then turn on the units, the master first. Once the master boots up and you are satisfied it's up and running, start turning other units one by one. Example of the configuration, for example, here a switch member 1, which is by default. We renumber this to 3, save and reboot. Go to the interface now, it becomes 3 because we renumbered, shut down, and we go to logical port 3.1, map that physical port to it, undo shutdown, save, and then perform this action. Once you issue this command, the switch reboots. So we'll try to join the stack and it will reboot. It might reboot again. Now the operating system has to be the same between different members in the stack. Display RF stack. You can see now we have this with 2 devices. One is a master with a priority 32 that has been left as default priority, and then we are connecting from member number 2, and this is the master as member number 1. A MAC persistent for 12 minutes, that will be the logical MAC address that will be advertised by both of these switches. Display configuration, you can see that's a different example, that this is daisy chain, but daisy chain 2 physical ports in 1 logical port. So in logical port number 1, on member 1, they have map 2 interfaces. In logical port 2, in member 2, they have map 2 interfaces. So logically, you have 1/1 port with 2 physical interfaces connecting to 2/2 logical port with 2 physical interfaces. You can look at the topology, display topology. Again, that's a different topology, and you can see there are 2, member ID 2, member ID 1. The neighbor for this one is 2, the neighbors of 2 is 1, and then it has this logical MAC address for the stack. that will mark the end of module 12, as well as it will mark the end of the training. Thank you very much for watching this training that consisted of 3 parts, and I'll see you in future trainings. Thank you very much.